Okay, so the ideal gas law. All right, let's see what this is. All right, so I just show you with the combined gas law that you can take Boyle's law, Gay-Lussac's law, and Charles' law, jam them together, and you get a new relationship for what's happening to a gas. But in that discussion, I completely excluded the number of moles, or more specifically, I excluded Avogadro's law from the relationship. The ideal gas law will incorporate Avogadro's law in addition to everything else. So, based on the premise that we had before for the combined gas law, we restate what the equation of the lines are for each one of these relationships. So, for Boyle's law, we have P times V equals the slope of the line. For Gay-Lussac's law, we have pressure over temperature equals the slope of the line. For Charles' law, we know that volume over temperature equals the slope of the line, and for Avogadro's law, we know that volume over moles equals the slope of the line. Okay, so notice the following. Pressure and volume, wherever they appear on the equations, are always on top of the fraction. Temperature and moles, wherever they appear in the equations, are always in the denominator. So if we bring all four of these equations together, we will always have the pressure and the volume on top, and we will always have the moles and the temperature on the bottom. And this will have to equal some other constant associated with this equation, which is technically in 4 dimensions now, right? But it's going to equal some constant. All right, now, unlike the combined gas law, we will not look for duets of data. So we will not have two pressures, two volumes, two moles, and two temperatures. Instead, we're going to go ahead and try to solve for the value of this constant, okay? And the way you do that is by looking at standard conditions, conditions that have been established a long time ago and agreed upon by scientists. We already discussed two of them in the combined gas law. We talked about standard temperature and standard pressure. The standard pressure is 1 atmosphere, but the ones that we haven't talked about are the volume and the moles. And it turns out to be the case that when you are dealing with 1 mole of gas, that mole of gas ideally occupies 22.4 liters worth of volume. This is something that has been found out experimentally. And the standard temperature we talked about in the combined gas law, it's 273 Kelvin. But yes, the number of moles is 1. That's the standard condition for a gas. Now, if you take each one of these 4 values, each one of these 4 standard values, the 1 atmosphere pressure, the 22.4 liters of gas occupied whenever you have 1 mole of gas, and the 273 Kelvin temperature, and you literally plug it into the equation, you have 1 atmosphere on top, 22.4 liters on top, 1 mole on the bottom, 273 Kelvin on the bottom. And notice that I have also boxed in pressure and temperature because those are your STP conditions, right? The ones I want you to really remember. When you plug in all of these values, the standard values, and carry out the calculation, you find out that the value of the constant is 0.08206 atmospheres times liters divided by mole Kelvin. This is the value of the ideal gas constant, and we refer to it with a specific letter, and that's the capital R. So capital R stands for 0.08206 atmosphere liters divided by mole Kelvin, and is the gas constant of the ideal gas law. So the last thing that happens is that we rearrange the equation here to have no denominator. So we cross multiply everything by moles times temperature, and we end up with pressure times volume equals moles times gas constant times temperature, or in other words, PV equals nRT. This right here is the ideal gas law. And the big difference between this law and all the other gas laws that we've talked about is that there is no sets of pressures, volumes, moles, temperatures. There's no sets of 2 pressures, 2 volumes, 2 moles, 2 temperatures. There's only just 1 pressure, 1 volume, 1 temperature, and 1 mole. And I'm going to show you an example in a little bit, but before I get ahead of myself, I need to discuss one additional factor. In the previous gas laws, we never bothered determining the value of the constant itself. But now we have a constant, and this constant has units. It has units of atmosphere liter per mole Kelvin. So what that means is that whenever we use the ideal gas law, the pressure will have to be in atmospheres, and the volume will have to be in liters. The same is true for N and T. N has to be moles, and T will always have to be Kelvin. Not Celsius, not Fahrenheit, but Kelvin. All right. So this is the one restriction that the ideal gas law instills within it as a result of having actually found the value of the constant itself, and the constant having units. You need those units to cancel out. All right. Now, two assumptions I'm going to point out right now. When we start talking about real gases, I'm going to readdress this issue. But one assumption that the ideal gas law makes is that the gases don't have a volume of their own. They are point particles, okay? So they do occupy space, and they certainly occupy volume, but you can change the volume at will, right? You can expand the volume or you can compress the volume. And the idea right here is that because the gases behave as point particles, they don't occupy a volume of their own, so you can make those changes happen. That's one assumption. The other assumption is that the gases themselves do not interact with one another. It's almost like they don't see each other. They act like zombies. And they don't necessarily do anything with each other. Now, as you'll find out in future videos, these two assumptions are actually wrong, but these are the assumptions under which the ideal gas law presides. All right, now let me show you an example of how the ideal gas law will look like, how we go about solving for something using the ideal gas law. And then I'm going to show you a set of derivations, and that will finish this video. All right, so here goes. We are being told that we have these cylinders of chlorine gas, 250 grams worth of chlorine gas stored in this cylinder. The cylinder is worth 150 liters in volume, and the cylinder itself is stored at room temperature, 25 degrees Celsius. What I want to find out is the pressure inside the tank. Okay, so notice that in this problem, we have been given the amount, not in moles, rather in grams, but it's still the amount of the gas. We have been given volume, we have been given temperature, and we're being asked for the pressure, but we don't have duets of any data. There is no dual volumes, dual temperatures, dual pressures, or dual moles. This is telling you that you have to use the ideal gas law because this is the only one where you don't need duets of data. And right here you're looking for pressure, so what you need to do is divide both sides by the volume. So you're going to be dealing specifically with this version. So pressure equals nRT divided by V. All right, so let's take that equation here. Oh, and by the way, we need moles, not grams. So we're going to have to change the grams to moles by using the molar mass of Cl2. We have grams on top, so we make sure to have grams on the bottom and moles on top, right? So this is the molar mass of Cl2. The grams will cancel out. Upon dividing 250 by 70.90, you'll end up with the moles of Cl2. Okay, also, you need to change the temperature to Kelvin. So 25 needs to be divided by 273 in order to get a temperature in Kelvin. Oh, and by the way, in future problems, whether you use the 0.15 or not is really not going to change the answer too much. So I'll leave that up to you. I generally just stick with 273, but 273.15 is also fine, in case you were wondering. All right, so we have the temperature in Kelvin, we have the number of moles, we have the volume in liters, so we're good to go. We just need to plug this into the equation. 3.526 moles, which we found out, 0.08206 atmosphere liter mole Kelvin, which is the gas constant, 298.15 Kelvin, which is the temperature, and 150 liters, which is the volume. Notice that the moles cancel out, the liters cancel out, and the Kelvin units cancel out. All that's left is atmospheres. So multiply 3.526 by 0.8206, multiply by 298.15, press enter, divide by 150, press enter, and you'll find out that the pressure is 0.5751 atmospheres. And that's in keeping with the significant figure since we have 4 sig figs in every single number here. All right, so that's the example. And the key idea right here is that if you only have one set, so you only have one volume, one temperature, one mole, one pressure, the ideal gas law is what you have to use. If you have duets of data, that's when you start dealing with the combined gas law or any of the 2D laws. And speaking of which, let me show you one additional factor that's actually kind of cool about the ideal gas law. The ideal gas law can in essence be used to derive all of the other laws, including the combined gas law, but due to the lack of space, I'm only going to stick to the 2D laws right here. But if you start with the premise that, okay, you have to have pressure volume relationship, pressure temperature relationship, volume temperature, and volume mole relationships for the corresponding 2D laws, what you can do is set up your ideal gas law, PV equals nRT, every single time. And all you need to do is, for whatever set of data, pressure, volume that you need for your 2D law, make sure that those two parameters are on the left side of the equation of the ideal gas law. So pressure, volume is what you need for Boyle's law. That's what you have on the left side of the equation. So this looks good. For Gillow-Sachs law, you need pressure and temperature. So what you need to do is move the temperature to the left side. In other words, divide both sides by temperature. But the volume cannot be there because you only need pressure and temperature. So you will have to divide both sides by volume. The same thing goes for Charles' law. You need volume and temperature, divide both sides by temperature, and divide both sides by pressure. And over here, you need volume and moles, so divide both sides by volume, divide both sides by pressure, and you will end up with the following parameter, right? So here we're dividing by the volume to isolate the pressure. Here we're dividing by pressure to isolate for the volume, and here we're dividing by the pressure to isolate again for the volume. Then we divide by the corresponding second parameter, temperature for Gillow-Sachs law, temperature for Charles' law, and moles for Avogadro's law. So now notice that we have P over T, V over T, V over N, and P over C, all equaling a constant, because for Gillow-Sachs law, Charles' law, Avogadro's law, everything that we left on the right side of the equation is a collection of constants. And the beauty of this is that from the ideal gas law, we have basically found out the relationships for Boyle's law, Gillow-Sachs law, Charles' law, and Avogadro's law. Namely that P times V must equal P times V. P over T must equal P over T. V over T must equal V over T. And V over N must equal V over N. So this is a really nice way of deriving all of the 2D laws without having to memorize them. And I recommend that you approach the problems this way. I personally will not give you the equations for Boyle's law, Gillow-Sachs law, Charles' law, and Avogadro's law in a problem, especially on the exam. So I recommend that you get familiar with how to derive the different laws using the ideal gas law. And with that, we'll finish this video.